Hey everyone, before we drift into the fascinating world of our atmosphere, where are you watching this video from and what time is it where you are? Maybe you're snuggled in bed, listening to the gentle hum of the night, or perhaps you're winding down after a long day, a cool breeze whispering at your window. Wherever you are, take a moment to really feel it. The warmth of your blanket, the air on your skin, the subtle shift in temperature as day turns to night. This, you might think, is just how the world is. But what if I told you that the very air you're breathing, the gentle breeze you feel, and the clouds slowly drifting across the sky are all part of a magnificent invisible dance, far more complex and intricately connected than you could possibly imagine? What if every drop of rain, every gust of wind, and every ray of sunshine is a tiny, incredibly intricate piece of a much larger, living system? Join us on a peaceful journey as we gently unfurl the secrets of the sky above us, from the tiniest water vapor molecules to the mightiest global winds. We're going to explore the hidden truths of our planet's atmosphere, challenge everything you thought you knew about a simple forecast, and ask the ultimate question: what if the weather isn't just something that happens to us, but a story written by forces we're only just beginning to truly understand? Imagine for a moment that you are an intrepid deep-sea diver, about to plunge into an ocean so vast, so profound, that its surface stretches beyond the horizon in every direction. Now picture that you are not preparing to descend into water, but rather to ascend into an even more immense and enigmatic ocean, the ocean of air that envelops our entire planet. This is not a mere void or an empty space. It is a tangible, dynamic, and incredibly powerful fluid, a grand, invisible sea that we, and indeed all life on Earth, are perpetually immersed within. We call this incredible fluid the atmosphere. From the moment you opened your eyes this morning, to the gentle flutter of a curtain in a passing breeze, to the powerful roar of a jet engine slicing through the sky, every single one of these experiences is a testament to the presence and profound influence of this atmospheric ocean. We take it for granted, breathing in and out approximately 20,000 times a day without a second thought. Yet within each breath lies a universe of intricate processes and forces that shape our world in ways we are only just beginning to truly appreciate. This isn't just nothingness above us. It is the very essence of our planet's living skin, a protective shield, a dynamic engine, and the stage upon which the grand drama of weather unfolds. Think about it. Have you ever stood on a blustery day, feeling the wind whip around you, pushing against your clothes, tugging at your hair? That's not an abstract force. That is the air in motion, asserting its presence. Or perhaps you felt the oppressive stillness of a hot, humid summer afternoon, where the air itself seems thick and heavy, almost tangible. That sensation too is the air, laden with an invisible passenger that we'll soon get to know. This vast, silent, and often imperceptible ocean of air is the fundamental canvas upon which all weather phenomena are painted. Without it, there would be no clouds to marvel at, no rain to nourish the earth, no storms to remind us of nature's raw power, and certainly no life as we know it. So what exactly is this air that we are so intimately connected with, yet so rarely consciously acknowledge? At its most basic, the air we breathe is a remarkable blend of invisible gases, a cocktail of elements perfectly balanced to sustain the intricate web of life on Earth. Imagine, if you will, a gigantic invisible stew constantly simmering and swirling around our planet. The main ingredients in this stew are nitrogen, oxygen, and argon. Nitrogen, remarkably, makes up the largest proportion, hovering around 78% of the air. It's a relatively inert gas, meaning it doesn't react much with other substances, and its primary role is to dilute the more reactive oxygen, helping to regulate the Earth's processes. Then there's oxygen, the life giver, comprising about 21%. This is the gas our bodies crave with every breath, the fuel for our internal furnaces, and the very reason most complex life forms can thrive on this planet. Without oxygen, our fires wouldn't burn, our cells wouldn't function, and our world would be an entirely different, desolate place. The remaining 1% is mostly argon, another inert gas, along with trace amounts of several others. These three, nitrogen, oxygen, and argon, form the stable scaffolding of our atmosphere. They are the constants, the unchanging framework upon which everything else builds. But here's where it gets truly fascinating, and where the story of weather truly begins to take shape. While nitrogen, oxygen, and argon are the bulk, the true star of our weather story, the most dynamic and influential ingredient in our atmospheric stew, is something you can't even see: water vapor. Unlike the fixed proportions of nitrogen and oxygen, the amount of water vapor in the air is constantly fluctuating, ranging from almost nothing in the driest deserts to as much as 4% in the most humid tropical environments. This tiny, seemingly insignificant component, this invisible gas form of water, is the very lifeblood of our weather system. It is the raw material for clouds, the source of all precipitation, and an incredibly powerful conductor and transporter of energy throughout the atmosphere. Without water vapor, there would be no rain, no snow, no fog, no dew, essentially no visible weather as we know it. It's the invisible artist, constantly reshaping the atmospheric canvas. Imagine a giant cosmic thermostat constantly adjusting itself. The primary way it does this is through the movement of this invisible water vapor. When water evaporates from oceans, lakes, rivers, or even from the leaves of plants, it doesn't just disappear, it transforms into this gaseous state, rising up into the atmosphere, carrying with it immense amounts of heat energy. This process is like charging a giant battery in the sky, a battery that will later release its energy in dramatic fashion, shaping everything from a gentle evening shower to a colossal hurricane. We'll delve much deeper into water's incredible journey later, but for now, simply appreciate its profound importance as the volatile, ever-changing ingredient that truly sets our atmospheric stage. Now let's consider another fundamental characteristic of this air-ocean: its weight. Yes, air has weight. It's easy to forget this because we're so accustomed to it. But just as water in an ocean exerts pressure on a diver, the deeper they go, the air above us exerts a constant pressure on everything beneath it. We call this atmospheric pressure. Think of it like this. Imagine a stack of invisible books stretching miles upwards from your head into space. Each book is a layer of air, and the sheer cumulative weight of all those layers pressing down creates the pressure we feel. At sea level, this pressure is roughly 14.7 pounds per square inch, which means that on every square inch of your body there's nearly 15 pounds of air pushing down. This might sound incredible, even crushing, but our bodies are perfectly adapted to it. We're essentially filled with air and fluids that exert an outward pressure, balancing the inward push. You experience the effects of atmospheric pressure regularly, even if you don't consciously recognize it. When you fly in an aeroplane and your ears pop as you ascend or descend, that's your body adjusting to the change in external air pressure. When you drink through a straw, you're not sucking the liquid up. You're actually reducing the air pressure inside the straw, allowing the greater atmospheric pressure on the surface of the liquid outside the straw to push the liquid up into your mouth. These are not magic tricks. They are direct demonstrations of the invisible hand of atmospheric pressure at work. And this pressure is not static. It is constantly changing, driven by the dynamic movements and properties of our atmospheric ocean. These shifts in pressure are in fact one of the primary drivers of wind, clouds, and storms, as air naturally flows from areas of higher pressure to areas of lower pressure, much like water flowing downhill. Finally, let's talk about the most intuitive property of air, yet one that holds immense power in the weather story: its temperature. Temperature, at its core, is simply a measure of how much energy the air molecules possess, how fast they are jiggling and bouncing around. When the air is warm, its molecules are energetic and spread out. When it's cold, they are sluggish and packed more closely together. This seemingly simple concept of warmth and cold is, in fact, the fundamental engine that drives all weather. Think of the sun, our ultimate energy source, constantly beaming down colossal amounts of energy onto our planet. But this energy doesn't hit the Earth uniformly. Some areas, like the equator, receive direct, intense sunlight, heating the air and land significantly. Other areas, like the poles, receive sunlight at a much shallower angle, distributing the energy over a larger area and resulting in far less heating. This uneven distribution of heat is the grand orchestrator of our weather. It sets up massive temperature differences across the globe, which in turn create pressure differences, which then drive the winds, which then transport moisture, and so on. It's an intricate, cascading chain reaction, all initiated by the sun's warmth and the Earth's uneven response to it. Imagine a giant pot of water on a stove. If you only heat one side of the pot, the water on that side will become warmer, lighter, and begin to rise, while the cooler, denser water on the other side will sink, creating a circulation current. Our atmosphere behaves in much the same way, but on a planetary scale. The sun heats one part of our atmospheric pot more than another, setting in motion colossal movements of air, redistributing heat, moisture, and pressure across continents and oceans. Temperature isn't just about whether you need a coat or a t-shirt. It's the very lifeblood of atmospheric circulation, the engine that powers every cloud, every storm, and every gentle breeze. So as we prepare to delve deeper into the intricate dance of our atmosphere, remember these fundamental truths. The air is not empty space, but a tangible, weighty ocean of gases. Its most dynamic ingredient, water vapor, is the invisible force shaping our skies. Its pressure, constantly shifting, dictates the movement of air, and its temperature, driven by the sun's uneven embrace, is the ultimate orchestrator of all weather. These aren't just scientific facts. They are the fundamental building blocks of the reality you experience every single moment, whether you're aware of it or not. And understanding them is the first step to truly appreciating the mind-bending complexity and profound beauty of the world above. We've only just begun to scratch the surface of this invisible ocean, and the incredible journey of discovery has only just started. Last time we painted a picture of the atmosphere as a vast, invisible ocean of air, a dynamic blend of gases with water vapor as its most volatile and fascinating ingredient. We touched upon how temperature differences are the grand orchestrators of atmospheric movement, but we merely hinted at the ultimate source of this energy. Now, let's pull back the curtain and reveal the true star of our celestial show, the colossal furnace at the heart of our solar system, without which none of the weather phenomena we experience would ever exist, the sun. It might seem obvious, even simplistic, to state that the sun powers our weather. After all, everyone knows the sun warms the earth, but the true depth of its influence, the intricate ways in which its energy is captured, transformed, and redistributed across our planet, is far more sophisticated and breathtaking than a casual glance would suggest. The sun isn't just a giant light bulb in the sky. It is the ultimate engine, the colossal battery charger, the ceaseless powerhouse that fuels every single cloud that drifts by, every rain shower that nourishes the land, every gentle breeze that rustles the leaves, and every ferocious storm that reminds us of nature's raw power. Without its relentless outpouring of energy, our world would be a frozen, desolate rock, devoid of the vibrant, ever-changing atmospheric drama we call weather. So how exactly does this distant star, millions upon millions of miles away, manage to exert such profound control over the local conditions in your backyard? It all begins with something called solar radiation. Imagine pure energy, traveling at the speed of light, beaming outwards from the sun in all directions. A tiny fraction of this immense energy reaches Earth in the form of sunlight, not just the visible light that allows us to see, but also invisible forms like ultraviolet UV radiation and infrared IR radiation, which we primarily perceive as heat. When this solar radiation reaches our planet, a remarkable transformation occurs. First, not all of the sun's energy makes it directly to the Earth's surface. Our atmosphere, that amazing protective blanket we discussed, plays a crucial role as a filter and a reflector. Some of the incoming solar radiation is scattered by gas molecules and tiny particles in the atmosphere, which is why the sky appears blue on a clear day. Some is reflected back into space by bright surfaces like clouds and ice caps, and a small portion is absorbed directly by atmospheric gases, particularly by water vapor and carbon dioxide. But the majority, a significant portion of this incoming solar energy, penetrates the atmosphere and reaches the Earth's surface, the land and the oceans. And this is where the real magic and the true engine of weather begins. When sunlight hits the Earth's surface, that energy is absorbed and converted into heat. Think about walking barefoot on a dark asphalt road on a sunny day. It gets scorching hot. Now imagine walking on a light concrete sidewalk. It's still warm, but noticeably cooler. This simple observation illustrates a fundamental principle. Different surfaces absorb and reflect solar energy differently. Darker surfaces like forests, oceans, and dark soil are excellent absorbers of solar radiation, converting much of it into heat. Lighter surfaces like snow, ice, and deserts are much better at reflecting solar radiation back into space. This differential absorption is a critical first step in creating the temperature variations that drive weather. But there's another layer to this complexity. Land and water heat up and cool down at dramatically different rates. Imagine placing a pot of water and a metal pan of sand on a stove at the same time. Which one gets hot faster? The sand, by far. Which one stays hot longer after you turn off the burner? The water. This simple demonstration reveals a profound truth about our planet. Land surfaces heat up and cool down much more quickly than bodies of water. Water has a higher specific heat capacity, meaning it takes a lot more energy to raise the temperature of a given amount of water by 1 degree compared to the same amount of land. This is why coastal regions often experience milder temperature swings than inland areas. The vast ocean acts like a giant temperature regulator, absorbing and releasing heat slowly, moderating the extremes of both summer and winter. This difference in how land and water respond to solar heating creates significant temperature contrasts, setting up crucial atmospheric pressure differences that, as we hinted at, are the very genesis of wind. Now let's zoom out from local heating and consider the planet as a whole. The most critical factor in how the sun powers our global weather patterns is something called uneven heating. This is perhaps the single most important concept in understanding why our planet has distinct climate zones, why there are strong winds, and why weather patterns are constantly in flux. Imagine a giant, perfectly spherical ball being illuminated by a flashlight. The part of the ball directly facing the flashlight gets the most intense light, concentrated over a small area. As you move away from that central point, the light rays become more spread out, covering a larger area, and thus becoming less intense per unit of surface area. Our Earth and the Sun operate on the same principle. The Sun's rays strike the Earth most directly and intensely at the equator. Here, the sunlight hits the surface almost perpendicularly, concentrating a massive amount of energy into a relatively small area. This is why equatorial regions are perpetually warm, moist, and often experience vigorous convection, warm air rising. As you move away from the equator towards the poles, the angle at which the sun's rays hit the Earth becomes increasingly oblique or slanted. The same amount of solar energy is spread out over a much larger surface area, greatly reducing its intensity per square foot. Furthermore, at higher latitudes, the sunlight has to travel through a greater thickness of atmosphere, meaning more of its energy is scattered and absorbed before it even reaches the ground. This combination of factors, the angle of incidence and the atmospheric path length, results in significantly less solar heating at the poles compared to the equator. This fundamental difference in solar heating between the equator and the poles is the primary driver of all global atmospheric circulation. Think of it as creating a gigantic planetary-scale temperature gradient, a massive difference in warmth from one part of the Earth to another. This enormous temperature imbalance constantly seeks to equalize itself, and the atmosphere, being a fluid, is the primary medium through which this equalization attempt occurs. Warm air, being less dense, rises at the equator, creating an area of lower pressure. Cooler, denser air at the poles sinks, creating areas of higher pressure. This inherent instability, this constant striving for balance, sets up the colossal air currents that tirelessly transport heat from the warm tropics towards the cold poles, and cold air from the poles back towards the equator. These are the vast invisible rivers of air that shape our climate and influence all local weather systems. And speaking of vast, the Earth isn't just a static sphere, it's a rapidly spinning top, completing a full rotation approximately every 24 hours. This rotation introduces another crucial layer of complexity to how solar energy is distributed and how atmospheric currents behave. Furthermore, our planet isn't spinning perfectly upright relative to its orbit around the Sun. The Earth's axis is tilted at an angle of approximately 23.5 degrees relative to its orbital plane. This tilt, seemingly a minor detail, is actually the reason we have seasons. As the Earth orbits the Sun throughout the year, different parts of the planet are tilted, either towards or away from the Sun. When the northern hemisphere is tilted towards the Sun, it receives more direct sunlight and experiences longer days, leading to summer. 6 months later, when the northern hemisphere is tilted away, it receives less direct sunlight and experiences shorter days, leading to winter. The southern hemisphere, of course, experiences the opposite seasons. This annual dance of the Earth's tilt around the Sun creates a profound rhythm in the amount of solar energy different regions receive over the course of a year, leading to dramatic seasonal shifts in temperature, pressure, and ultimately, weather patterns. From the scorching heat of summer to the biting cold of winter, every seasonal variation you experience is a direct consequence of this celestial ballet between the Earth's tilt and its orbit around its solar engine. So, to truly grasp how weather works, we must first bow to the Sun. It is the ultimate instigator, the tireless power source that injects energy into our atmospheric system. Its uneven distribution across the globe, due to the Earth's spherical shape and its axial tilt, creates the fundamental temperature gradients. These gradients, in turn, are the wellspring of pressure differences, which then drive the movement of air, the wind, and initiate the grand atmospheric circulation patterns that redistribute heat and moisture across the planet. Every cloud formation, every storm's fury, every calm day, every temperature fluctuation can ultimately trace its lineage back to a photon of sunlight striking our planet. The Sun doesn't just warm us, it choreographs the entire atmospheric symphony, setting the stage for the incredible journey of water, which is precisely where our next chapter will take us. We've seen the engine. Now let's explore its most active and transformative passenger. We've established the Sun as the undeniable engine of our weather, continuously pumping colossal amounts of energy into our atmosphere, creating those fundamental temperature differences across the globe. We understand that this uneven heating initiates a grand, planetary-scale effort to balance itself out, a process that involves the constant motion of our atmospheric ocean. But there is a crucial, ever-present element within that ocean, an invisible and sometimes visible passenger that elevates the Sun's raw energy into the breathtaking displays we call weather. This is water, in all its incredible forms, engaged in a perpetual, shape-shifting dance known as the hydrologic cycle, or, more simply, water's wild ride. If the atmosphere is the stage and the Sun is the spotlight, then water is undoubtedly the lead performer, constantly changing costumes and delivering the most dramatic acts. Think about any significant weather event: a gentle spring shower, a misty morning fog, a towering thunderstorm, a blanketing snowstorm, or the devastating power of a hurricane. What do all these have in common? Water. It is the transformative agent, the medium through which much of the Sun's energy is transported and released, the very essence of how our skies come alive. Without water constantly moving through its different states, liquid, solid, and gas, our atmosphere would be a dry, static, and largely uneventful place, and our planet would be barren. The first, and perhaps most subtle, act in water's journey is evaporation. We touched upon water vapor as the dynamic ingredient in our atmospheric stew. But how does water get into the air in the first place? Imagine a puddle on the sidewalk after a rain shower. As the sun shines down, or even on a dry, breezy day, that puddle gradually shrinks and eventually disappears. It doesn't magically vanish, it transforms. The liquid water absorbs energy, primarily from the sun, but also from the surrounding air, causing its molecules to vibrate faster and faster, until some of them gain enough energy to break free from the liquid surface and float upwards, becoming individual, invisible gas molecules of water vapor. This process happens constantly from every body of water on Earth: oceans, lakes, rivers, even puddles. But the vast majority of water vapor in the atmosphere comes from the enormous surface area of the world's oceans, tirelessly absorbing solar energy and releasing countless trillions of water molecules into the air. Plants also contribute significantly through a process called transpiration, where water vapor is released from their leaves into the atmosphere. Forests, especially vast ones like the Amazon rainforest, act like giant living pumps, moving incredible volumes of water from the ground into the air. So evaporation isn't just a physical process, it's a biological one too, a testament to the interconnectedness of Earth's systems. When water evaporates, it takes a substantial amount of heat energy with it, effectively cooling the surface from which it evaporated. This hidden heat, known as latent heat, isn't lost, it's now stored within the invisible water vapor molecules, a kind of atmospheric energy currency, poised to be released later in the cycle. This storage and release of latent heat is absolutely fundamental to understanding how clouds form and how storms gain their immense power. As these invisible water vapor molecules rise, carried by the warmth and upward currents in the air, they eventually reach higher altitudes where the atmospheric pressure is lower, and crucially, the temperature is colder. This leads us to the next mesmerizing act, condensation. Imagine taking a cold glass out of the refrigerator on a humid day. Within moments, tiny droplets of water form on its surface. Where did that water come from? It came from the invisible water vapor in the air around the glass, which cooled down upon contact with the cold surface, causing the water vapor molecules to slow down, lose energy, and clump together, returning to their liquid state. In the atmosphere, a similar process occurs, but on a grander scale. As warm, moist air rises, it expands because there's less pressure pushing down on it. As it expands, it cools. This cooling is critical because cooler air can hold less water vapor than warmer air. Think of it like a sponge that gets squeezed. As the air cools, its capacity to hold water vapor diminishes. Eventually, the air cools to its dew point, the temperature at which it becomes saturated, unable to hold any more water vapor. When this happens, the excess water vapor begins to condense, transforming back into incredibly tiny liquid water droplets, or if it's cold enough, ice crystals. But here's a crucial detail. These water vapor molecules need something to condense on. They don't just spontaneously form droplets in empty air. They need microscopic particles floating in the atmosphere: dust, pollen, smoke, sea salt, even exhaust particles. These are called condensation nuclei. Each tiny water droplet or ice crystal forms around one of these microscopic particles, acting as a seed for condensation. When billions upon billions of these microscopic water droplets or ice crystals form close together, suspended in the air, they become visible to our eyes. And what do we see when billions of these tiny droplets and crystals aggregate? We see clouds. Clouds are not simply aesthetic decorations in the sky. They are direct visual manifestations of atmospheric processes at work, massive factories of condensation, and ultimately, precipitation. The type of cloud we see tells us a story about the conditions in the atmosphere. The fluffy, fair-weather cumulus clouds, often described as cotton balls, are formed by rising pockets of warm air. The vast, flat stratus clouds, which can cover the entire sky and bring drizzle, form when large layers of air are lifted slowly. And the towering cumulonimbus clouds, often shaped like anvils, are the powerhouses of the atmosphere, indicating intense vertical air movement, massive amounts of condensation, and the potential for severe weather. Every cloud is a temporary visible reservoir of condensed water, patiently awaiting its next transformation. As these tiny cloud droplets or ice crystals continue to grow, through collision and coalescence, they eventually become too heavy for the air currents to support them. This leads us to the culmination of water's journey, precipitation. When the droplets or crystals grow large enough, gravity takes over, and they fall to the Earth's surface. This can take many forms, depending on the temperature profile of the atmosphere from the cloud down to the ground. If the entire column of air is above freezing, the precipitation falls as rain. If it's cold enough throughout the entire column, it falls as snow, beautiful hexagonal ice crystals. If there's a layer of freezing air near the ground, but warmer air above, it might fall as sleet, ice pellets, or freezing rain, which freezes on contact with surfaces, coating everything in a treacherous layer of ice. And in powerful thunderstorms, strong updrafts can carry raindrops high into the very cold upper atmosphere, where they freeze into ice pellets. These pellets can then gather more layers of ice as they are repeatedly carried up and down by strong winds within the cloud. eventually falling as hail, sometimes as small as peas, other times as large as golf balls or even softballs, capable of causing immense damage. Once precipitation reaches the Earth's surface, its journey continues. It might infiltrate the ground, becoming groundwater, slowly making its way through underground aquifers. It might run off into streams, rivers, and eventually back to lakes or the ocean, a process called runoff. It might evaporate again directly from the surface, or be taken up by plants and transpired back into the atmosphere. Or, if it falls as snow or ice, it might accumulate in glaciers or snowpacks, remaining frozen for weeks, months, years, or even centuries, only to melt later and rejoin the cycle. This entire continuous loop, evaporation, condensation, precipitation, and collection, is what we call the hydrologic cycle. It's a closed system. The amount of water on Earth remains essentially constant, but it is perpetually moving, changing state, and redistributing itself across the planet, driven relentlessly by the sun's energy. The sheer volume of water involved in this cycle is almost unfathomable. Every day, trillions of gallons of water evaporate from the oceans alone, rise into the atmosphere, condense into clouds, and eventually fall back as precipitation somewhere on Earth. This constant circulation of water is not just about producing rain for our crops or snow for our winter sports. It is absolutely vital for distributing heat energy around the globe. When water evaporates, it absorbs latent heat, effectively transferring heat from the surface into the atmosphere. When it condenses to form clouds and precipitation, it releases that latent heat, warming the surrounding air. This release of latent heat is a major energy source for thunderstorms and hurricanes, providing the fuel that allows them to grow into powerful destructive forces. So, water is not just a passive passenger in our atmospheric ocean. It is an active, energetic participant, constantly transforming and transporting energy, making visible the invisible workings of the atmosphere. From the seemingly empty air around us, to the vast, majestic clouds floating high above, to the life-giving rain that falls to the ground, every aspect of water's wild ride is a direct consequence of the interplay between the sun's energy and the fundamental properties of air. We've seen how the sun sets the stage and how water performs its endless cycle. But what about the invisible force that truly pushes and pulls these elements, the great orchestrator of movement that ensures this show never stops? That, as we shall see, is the ever-present, sometimes gentle, sometimes ferocious phenomenon of wind. We've explored the sun as the colossal engine providing the raw energy, and water as the incredible shapeshifter, tirelessly moving through its cycle, absorbing and releasing vast quantities of heat. But what connects these two fundamental elements? What is the invisible force that pushes the warm, moist air upwards, carries the newly formed clouds across vast distances, and brings the life-giving rain or the fierce, destructive storm to our doorsteps? That force, the true workhorse of the atmosphere, is the wind. It is the Earth's great breath, a constant, often imperceptible, sometimes overwhelming, testament to the atmosphere's relentless drive to achieve balance. Most of us think of wind simply as moving air, and while that's accurate, it barely scratches the surface of its profound importance. Wind is not just a random gust or a gentle breeze. It is a direct consequence of the fundamental principles we've already laid out. Remember how we discussed atmospheric pressure, the weight of the air above us, and recall how the sun's uneven heating creates temperature differences across the globe. These two concepts are inextricably linked, and their interaction is the very genesis of wind. At its core, wind is simply air flowing from an area of higher atmospheric pressure to an area of lower atmospheric pressure. It's a very simple concept, much like water flowing downhill. Water doesn't flow uphill on its own. It always moves from a higher elevation to a lower one, driven by gravity. Similarly, air doesn't flow from a low-pressure zone to a high-pressure zone. It always moves from where there's more air pushing down to where there's less air pushing down. The steeper the pressure difference over a given distance, the faster and stronger the wind will blow, much like a steeper hill produces a faster flow of water. This difference in pressure is what meteorologists call a pressure gradient. But what creates these areas of high and low pressure in the first place? This is where the sun's uneven heating and the subsequent temperature differences we explored come into play. When the sun heats the Earth's surface, the air directly above that warmed surface also heats up. As air warms, its molecules become more energetic, move faster, and spread out, making the air less dense. Less dense air is lighter, and just like a hot air balloon, it begins to rise. As this warm, lighter air rises, it effectively removes some of the weight from the column of air below it. This upward movement of air reduces the pressure at the surface, creating an area of low pressure. Think of it as a vacuum forming at the bottom of the rising column. Conversely, in areas where the air is colder, its molecules are less energetic and more closely packed together, making the air denser and heavier. This cold, dense air sinks towards the Earth's surface. As it descends, it adds to the weight of the column of air below it, increasing the pressure at the surface. This creates an area of high pressure. So in essence, high-pressure systems are generally associated with sinking air, which typically leads to clear, stable weather conditions, because the sinking air discourages cloud formation. Low-pressure systems, on the other hand, are generally associated with rising air, which cools, condenses, and forms clouds, often leading to stormy or unsettled weather. It's crucial to understand that these high and low-pressure systems are not static. They are constantly shifting, expanding, contracting, and moving across the Earth's surface, driven by the ongoing unequal distribution of solar energy. And it is the boundary between these high and low pressure systems, that pressure gradient, that truly dictates the strength and direction of the wind. When these pressure differences are small, the winds are light. When they are large and tightly packed together, as often happens in intense storm systems, the winds can become incredibly strong and destructive. Now, if the Earth were a non-rotating, perfectly smooth sphere, air would simply flow in straight lines from the perpetually warm equator to the perpetually cold poles, and then return along the surface. But our Earth, as we know, is anything but static. It is a rapidly spinning planet, completing a full rotation every 24 hours. This rotation introduces a fascinating and profoundly important effect on anything that moves freely over its surface, including vast currents of air and ocean water. This effect is known as the Coriolis effect. Imagine standing on a giant merry-go-round that is slowly spinning. If you try to roll a ball straight across the merry-go-round to a friend directly opposite you, the ball won't go in a straight line relative to the merry-go-round surface. Instead, it will appear to curve. From the perspective of someone standing off the merry-go-round, the ball travels in a straight line, but because the merry-go-round itself is rotating beneath the ball, it appears to deviate. The Earth's rotation has a similar, massive influence on global winds. In the northern hemisphere, the Coriolis effect deflects moving objects like air currents to their right. In the southern hemisphere, it deflects them to their left. This seemingly subtle deflection is monumental in shaping global wind patterns. Instead of air flowing in straight lines from high to low pressure, it gets bent, creating swirling circular patterns around high and low pressure systems. This is why low-pressure systems like hurricanes and mid-latitude cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, and high-pressure systems spin in the opposite direction. The Coriolis effect doesn't cause wind. It merely modifies its direction once it starts moving due to pressure differences. It's the invisible hand that steers the global atmospheric currents. These fundamental principles of pressure gradients and the Coriolis effect combine to create the magnificent system of global wind belts that crisscross our planet. These are not just random air movements. They are vast, persistent patterns of atmospheric circulation that transport heat and moisture around the globe, profoundly influencing regional climates and weather. Let's briefly envision these colossal conveyor belts of air. At the equator, where intense solar heating causes warm, moist air to rise, creating a persistent band of low pressure, this rising air eventually cools, spreads out, and moves poleward in the upper atmosphere. Around 30 degrees latitude north and south of the equator, this air, now cooler and denser, begins to sink back towards the surface, creating persistent bands of high pressure. These high pressure zones are often associated with dry, stable conditions, which is why many of the world's major deserts are located at these latitudes. As this air sinks, some of it flows back towards the equator, driven by the pressure gradient. But because of the Coriolis effect, these winds are deflected, forming the trade winds, historically crucial for sailing ships, blowing steadily from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. These are the winds that powered ancient exploration and continue to influence tropical weather, including the paths of hurricanes. Meanwhile, some of the air from those 30-degree high-pressure zones flows poleward. As it moves towards higher latitudes, it encounters colder air masses originating from the poles. Around 60 degrees latitude north and south, these contrasting air masses meet, creating zones of low pressure and frontal activity, often associated with significant storms. The winds in these mid-latitudes, again deflected by the Coriolis effect, are known as the westerlies, blowing predominantly from west to east. These are the prevailing winds that bring much of the weather to North America and Europe, constantly shifting and bringing periods of unsettled weather. Above the poles themselves, extremely cold, dense air sinks, creating persistent high-pressure zones, and from these, the polar easterlies flow away from the poles towards the mid-latitudes. These three major circulation cells in each hemisphere, the Hadley cell, tropics, the Ferrel cell, mid-latitudes, and the polar cell, along with the powerful high-altitude ribbons of fast-moving air known as jet streams, comprise the intricate, interconnected system of global winds. Jet streams are particularly important because they are narrow, meandering rivers of strong winds that occur at high altitudes, primarily separating cold air masses from warm air masses. Their position and strength greatly influence the paths of storms and the movement of weather systems across continents. A shift in the jet stream can bring a brutal cold snap to one region, while another experiences unusually warm temperatures. Understanding these global wind patterns isn't just an academic exercise. It's fundamental to understanding the climate of different regions, the long-range movement of pollutants, and the trajectories of major storms. These winds are constantly, tirelessly working to redistribute the sun's energy from the overheated equator to the underheated poles, a planetary-scale effort to balance the thermal budget. They are the invisible arteries and veins of our atmosphere, carrying not only heat, but also vast quantities of moisture, linking weather events across continents and oceans. From the gentle rustle of leaves to the destructive roar of a tornado, every breath of wind is a manifestation of these fundamental forces at play, a constant reminder of the atmosphere's dynamic nature and its endless quest for equilibrium. And while the winds are constantly moving air, often bringing new conditions, it is their interaction with the moisture we previously discussed and the intensification of these processes that truly brings forth the most dramatic and sometimes terrifying aspects of weather, the storms. The stage is set, the elements are active, and now we must delve into the most intense expressions of their interaction. We've explored the atmosphere as a dynamic fluid, propelled by the sun's energy and animated by water's ceaseless transformations. We've unraveled the invisible hand of wind, driven by pressure gradients and steered by the Earth's rotation, constantly working to equalize planetary temperature imbalances. These fundamental principles, the very bedrock of our weather system, typically manifest as the everyday conditions we experience: a sunny day, a gentle breeze, a steady rain. But when these ingredients, heat, moisture, and air movement, combine under just the right, or perhaps more accurately, the wrong conditions, they can coalesce into something far more powerful, more dramatic, and often more awe-inspiring, and sometimes terrifying: storms. These are the atmosphere's most intense expressions, moments when its inherent energy is unleashed with spectacular and sometimes devastating force. Storms are not random acts of nature. They are intensified versions of the processes we've already discussed, pushed to their limits by specific atmospheric configurations. Think of it like a pressure cooker. The same basic elements are inside, but when the heat and pressure build sufficiently, the results are explosive. Our atmosphere is a vast, self-regulating system, and storms are often its way of releasing pent-up energy, correcting imbalances, or shedding excess heat and moisture. Understanding them isn't just about predicting danger, it's about appreciating the raw, untamed power that lies within the very air we breathe. Let's begin with perhaps the most common and universally recognized severe weather phenomenon, the thunderstorm. You've undoubtedly seen them, towering, dark clouds, often with flat bases and anvil-shaped tops, accompanied by the dramatic symphony of lightning and thunder. But what makes a simple cumulus cloud transform into such an electrifying powerhouse? 3 ingredients are typically essential: moisture, instability, and a lifting mechanism. First, moisture. As we discussed in Water's Wild Ride, plentiful water vapor in the atmosphere provides the fuel. Thunderstorms thrive in warm, humid environments where there's an abundance of invisible water ready to condense. This moisture is absorbed as latent heat during evaporation, creating a vast reservoir of energy in the air. Second, instability. This refers to the atmosphere's tendency to resist or encourage vertical motion. Imagine a balloon filled with warm air. If you release it, it will rise because it's lighter than the surrounding air. The atmosphere behaves similarly. If a parcel of air is warmer and therefore less dense than the air around it, it will continue to rise. This condition is called atmospheric instability. The greater the temperature difference between a rising air parcel and its surroundings, the more unstable the atmosphere, and the more vigorously that air parcel will accelerate upwards. Thunderstorms require significant instability, often fueled by intense surface heating on a hot summer day, which creates buoyant, rapidly rising air currents. Third, a lifting mechanism. Even with abundant moisture and instability, air often needs a trigger to start its upward journey. This lifting can come from various sources: differential heating of the land, forcing air upwards; the convergence of air masses, where air flows towards a central point and has nowhere to go but up; orographic lift, where air is forced upwards as it encounters mountains; or most commonly and powerfully for severe thunderstorms, from weather fronts. When a colder, denser air mass pushes into a warmer, lighter air mass, a cold front, the cold air acts like a wedge, forcing the warm, moist air ahead of it rapidly upwards, initiating the powerful updrafts essential for thunderstorm development. Once these 3 ingredients combine, a thunderstorm begins to develop. Warm, moist, unstable air rapidly rises, carrying that immense latent heat energy upwards. As it rises, it cools, and the water vapor condenses, forming a towering cumulus cloud. This condensation releases the latent heat, warming the rising air even further and making it even more buoyant, accelerating its ascent. This positive feedback loop creates the powerful updrafts that are the hallmark of a thunderstorm, pulling more and more warm, moist air into the storm. As the updraft continues to build, it can reach the top of the troposphere, the lowest layer of the atmosphere where most weather occurs, where it hits a stable layer called the tropopause. Unable to rise further, the cloud spreads out horizontally, forming the characteristic flat, anvil-shaped top that indicates a mature thunderstorm. Within these towering clouds, a furious internal battle ensues. As water droplets and ice crystals are tossed around by the powerful updrafts and downdrafts, they collide repeatedly. These collisions lead to a separation of electrical charges, with positive charges typically accumulating at the top of the cloud and negative charges at the base. When this charge difference becomes large enough, the atmosphere can no longer act as an insulator, and a massive electrical discharge occurs. Lightning. Lightning can strike within the cloud, between clouds, or, most dramatically, from the cloud to the ground. The incredible heat of a lightning bolt, up to 30,000 degrees Celsius, 5 times hotter than the surface of the sun. This rapid expansion creates a powerful shock wave that travels outward as sound, thunder. Since light travels much faster than sound, we see the lightning flash almost instantly, but hear the thunder seconds later, the delay indicating how far away the strike occurred. Thunderstorms, while common, can vary greatly in intensity. Some are single-cell, brief, and relatively harmless, bringing a quick burst of rain and a rumble of thunder. Others can evolve into multi-cell thunderstorms, where new cells constantly form, creating longer-lasting and more widespread areas of heavy rain, lightning, and strong winds. But the most dangerous and awe-inspiring type is the supercell thunderstorm. These are highly organized, long-lived thunderstorms, characterized by a deep, persistent rotating updraft called a mesocyclone. This rotation gives supercells the potential to produce truly severe weather, including very large hail, damaging straight-line winds, and most famously and terrifyingly, tornadoes. Which brings us to the planet's most violent atmospheric vortex, the tornado. Born from the heart of powerful thunderstorms, particularly supercells, tornadoes are rapidly rotating columns of air that extend from the base of a cumulonimbus cloud to the ground. Their destructive power, despite their relatively small size, is immense, capable of tearing apart homes, lifting vehicles, and causing catastrophic damage in their path. The conditions for tornado formation are incredibly specific and complex, but generally involve strong wind shear, a significant change in wind speed and/or direction with height in the atmosphere. This wind shear can create horizontal tubes of rotating air. Within a supercell, the powerful updraft can then tilt this horizontal rotation vertically, pulling it upwards and strengthening it, creating that rotating mesocyclone. If this rotation tightens and intensifies, and if the mesocyclone extends down to the ground, a visible funnel cloud emerges and a tornado is born. The winds within a strong tornado can exceed 200 or even 300 miles per hour, creating a terrifying vacuum and a maelstrom of debris. Moving from the land to the vast oceans, we encounter the most powerful and largest storm systems on Earth, tropical cyclones, known by different names depending on where they form, hurricanes in the Atlantic and Northeast Pacific, typhoons in the Northwest Pacific, and cyclones in the South Pacific and Indian Ocean. These colossal rotating storm systems are essentially giant heat engines fueled by the warm, moist air evaporating from tropical oceans. For a tropical cyclone to form, several conditions must be met. First, very warm ocean waters, at least 26.5 kuk or 80 Fef. Third, light winds in the upper atmosphere are necessary, as strong winds can shear off the top of the storm, disrupting its organization. Finally, a pre-existing disturbance, like a cluster of thunderstorms or a tropical wave, is often the seed from which a cyclone develops, and a sufficient Coriolis effect is needed to initiate the rotation. This means tropical cyclones rarely form very close to the equator, as the Coriolis effect is weakest there. Once these conditions align, warm, moist air rapidly rises from the ocean surface, creating a central area of extremely low pressure. As this air rises and cools, massive amounts of water vapor condense, forming towering thunderstorm clouds that spiral around a central eye. The condensation process releases enormous quantities of latent heat, which further warms the surrounding air, making it even more buoyant and causing it to rise faster, pulling in even more warm, moist air from the ocean surface. This creates a powerful positive feedback loop that intensifies the storm. The Coriolis effect causes the incoming air to spiral inward towards the low-pressure center, giving the entire system its characteristic rotating appearance. In the northern hemisphere, hurricanes rotate counterclockwise. In the southern hemisphere, they rotate clockwise. At the very center of a mature hurricane is the eye, a relatively calm, clear area where air is actually sinking. Surrounding the eye is the eye wall, a ring of intensely strong thunderstorms with the hurricane's strongest winds and heaviest rainfall. Beyond the eye wall are spiral rain bands, extending outwards for hundreds of miles, bringing additional rain and wind. Tropical cyclones are categorized by their sustained wind speeds. Their destructive power comes not only from their extreme winds, but also from the torrential rainfall they produce, leading to widespread flooding, and most devastatingly, from the storm surge. This is a powerful, abnormal rise of water generated by the storm's winds pushing water towards the shore, often far exceeding normal tide levels and capable of inundating vast coastal areas. The immense scale and sheer energy of these systems are humbling reminders of the ocean's influence on our atmosphere. Finally, let's consider another type of storm, perhaps less dramatic than a hurricane, but equally impactful, especially in higher latitudes: winter storms. These are complex systems that bring a combination of freezing rain, sleet, heavy snow, and strong winds, often leading to blizzard conditions. Unlike thunderstorms, which are driven by convective uplift, winter storms are typically associated with large-scale frontal systems, especially those that involve the collision of very cold Arctic or polar air masses with warmer, moisture-laden air. The key ingredients for a significant winter storm are a supply of cold air, often originating from polar regions, a source of moisture, often from oceans or large bodies of water, and a lifting mechanism to force the moist air upwards, leading to condensation and precipitation. The type of precipitation received during a winter storm depends crucially on the temperature profile of the atmosphere from the clouds down to the ground. If the entire column of air is below freezing, it snows. If there's a shallow layer of freezing air near the surface with warmer air above, it can lead to freezing rain. If there are alternating layers of freezing and thawing, it can produce sleet. Blizzards, the most severe type of winter storm, are characterized by sustained winds or frequent gusts of 35 miles per hour or more, combined with falling or blowing snow, reducing visibility to a quarter mile or less for at least 3 hours. It's not just the amount of snow, but the wind and visibility that define a blizzard, making travel impossible and creating life-threatening conditions. The raw, biting cold, combined with driven snow, can lead to rapid hypothermia and frostbite. In essence, whether it's a crackling thunderstorm, a spiraling tornado, a monstrous hurricane, or a blinding blizzard, all these spectacular and often fearsome displays of nature's power are simply the atmosphere's way of expressing its internal dynamics. They are intense, concentrated efforts to redistribute the heat and moisture imbalances created by the sun's uneven embrace and the Earth's constant movement. They are powerful reminders of the continuous energy flow within our atmospheric ocean, a system that, while seemingly benign on a calm day, holds within it the potential for astonishing fury. Having now explored the major players and their most dramatic performances, the stage is set for us to move from observing these incredible phenomena to the intricate science of anticipating them. We've seen the incredible processes at work, and now we must turn to the human endeavor of trying to decipher and predict their unfolding story. We've journeyed through the invisible ocean of air, understood the sun as its primary energy source, followed water through its transformative cycle, and witnessed the powerful dynamics of wind and the dramatic intensity of storms. We've peeled back the layers, revealing the intricate dance of physics and chemistry that shapes every moment of our atmospheric experience. Now, having grasped the fundamental principles that govern our weather, a natural and compelling question arises: how do we, mere mortals, attempt to decipher this complex, ever-unfolding atmospheric narrative and predict what it will do next? How do meteorologists, those enigmatic figures on our screens, manage to tell us whether to expect sunshine or showers, a gentle breeze or a raging storm, sometimes days in advance? This leads us to the fascinating, continuously evolving science of weather forecasting. For centuries, predicting the weather was largely based on folklore, observation of natural signs, and a healthy dose of guesswork. Farmers would look at cloud formations, sailors would interpret wind shifts, and people would develop rhymes about red skies at night. While these traditional methods held nuggets of truth born from accumulated experience, they lacked the systematic scientific rigor needed for reliable prediction. The true dawn of modern weather forecasting, however, is a relatively recent phenomenon, one that has been revolutionized by technological advancements and a deeper understanding of atmospheric physics. At its heart, weather forecasting is an enormous, continuous detective story, where the atmosphere itself is the ever-changing crime scene. To solve this mystery, meteorologists need clues, vast amounts of them, about the current state of the atmosphere. This quest for data begins with a global network of sophisticated instruments, constantly observing, measuring, and reporting atmospheric conditions from every conceivable vantage point. Imagine a giant global tapestry woven with countless threads of data, each one a measurement of temperature, pressure, humidity, wind speed, or wind direction. These threads come from a multitude of sources. On the ground, thousands of automated weather stations are scattered across every continent, dutifully recording conditions at fixed locations. These stations, often located at airports or in open fields, provide a continuous stream of surface observations, which are the foundation for understanding local weather. Ascending into the atmosphere, we find weather balloons, released twice a day at midnight and noon UTC, from hundreds of locations around the world. These helium or hydrogen-filled balloons carry small instrument packages called radiosondes, which measure temperature, humidity, and pressure as they ascend, transmitting the data back to ground stations. As the balloon is carried by the wind, its position can also be tracked, providing vital information on wind speed and direction at various altitudes. These vertical profiles of the atmosphere are absolutely critical, revealing how conditions change with height, information that is essential for understanding atmospheric stability, the potential for thunderstorms, and the structure of large-scale weather systems. High above the Earth, a fleet of weather satellites provide an unparalleled bird's-eye view of our planet's atmosphere. These silent sentinels, orbiting at different altitudes, collect a staggering amount of data, far beyond what ground stations and balloons can provide. Geostationary satellites hover above a fixed point on the equator, providing continuous, real-time images of cloud cover, storm development, and atmospheric moisture across vast regions. Polar orbiting satellites circle the Earth from pole to pole, capturing high-resolution images and data that fill in the gaps, especially over oceanic and polar regions not covered by geostationary satellites. Satellites don't just take pictures, they use various sensors to measure sea surface temperatures, atmospheric temperature, and humidity profiles, even the height of cloud tops, providing invaluable insights into the invisible workings of the atmosphere. Then there's radar, a technology that allows us to peer inside clouds and see what's happening. Doppler radar systems send out microwave pulses that bounce off precipitation particles, raindrops, snowflakes, hail, within clouds. By analyzing the time it takes for the signal to return and the shift in its frequency, the Doppler effect, meteorologists can determine the location, intensity, and even the movement of precipitation. This is how forecasters can pinpoint areas of heavy rain, track the movement of thunderstorms, and even detect the rotation within a supercell that might indicate the formation of a tornado. Weather radar is a crucial tool for short-term forecasting and severe weather warnings, giving communities precious minutes to prepare. Even ships at sea and commercial aircraft contribute to this vast data network, providing vital observations over oceans and at cruising altitudes, filling in critical gaps in global coverage. All of this raw data, from countless sources, streams into powerful supercomputing centers around the world, creating a near real-time snapshot of the global atmosphere. This massive influx of current atmospheric data is then fed into the heart of modern weather forecasting, numerical weather prediction models. These are incredibly complex computer programs that use sophisticated mathematical equations based on the fundamental laws of physics that govern fluid motion, thermodynamics, and atmospheric chemistry to simulate how the atmosphere will evolve over time. Think of it like this: if you know the exact position and velocity of every billiard ball on a pool table, and you know the forces acting on them, you could in theory predict their future positions. The atmosphere is infinitely more complex, but the principle is similar. The models take the current atmospheric state, the initial conditions, as input, and then, step by step, calculate how temperature, pressure, wind, and moisture will change at thousands or even millions of points in a three-dimensional grid that covers the entire globe. These models run on some of the most powerful supercomputers on Earth, crunching quadrillions of calculations per second. Different meteorological centers around the world, like the European Center for Medium-Range Weather Forecasts or the US National Oceanic and Atmospheric Administration, run their own versions of these models, each with slightly different equations, resolutions, and ways of representing atmospheric processes. This is why you sometimes hear slightly different forecasts from different sources. They might be using different models or different interpretations of the model output. Despite their incredible sophistication, these models are not perfect. The atmosphere is a chaotic system, meaning that tiny, imperceptible differences in the initial conditions can lead to vastly different outcomes over time. This is often referred to as the butterfly effect, the idea that a butterfly flapping its wings in Brazil could theoretically set off a tornado in Texas weeks later. While a poetic exaggeration, it highlights the inherent sensitivity and complexity of the atmosphere. Because we can never know the precise state of the atmosphere at every single point with absolute certainty, there will always be a degree of uncertainty in our initial conditions. This is why forecasts become less accurate the further out in time they go. A forecast for the next 12-24 hours is generally quite reliable, but a forecast for 7 to 10 days out carries significantly more uncertainty. This inherent uncertainty leads us to the crucial role of the human element in forecasting. While supercomputers provide the raw predictions, it is the skilled meteorologist who acts as the interpreter, the quality controller, and the final decision maker. Meteorologists don't just blindly read a computer printout. They analyze multiple model runs, look for inconsistencies, understand the strengths and weaknesses of different models, and apply their experience and knowledge of local geography and atmospheric dynamics to refine the forecast. They consider factors that models might struggle with, like localized terrain effects, and integrate real-time observations from radar and satellite. They translate complex model output into understandable language for the public and issue warnings when severe weather is expected. Their judgment, honed by years of training and experience, is invaluable in providing the most accurate and actionable weather information. This brings us to understanding probability and uncertainty in forecasts. When a meteorologist says there's a 30% chance of rain, they're not saying it will rain in 30% of your area, nor are they saying it will rain for 30% of the day. They are expressing a confidence level based on the models and their interpretation. There is a 30% probability that measurable precipitation, typically 0.01 inches or more, will fall at any given point in the forecast area during the specified time period. This might sound subtle, but it's a crucial distinction. It acknowledges the inherent uncertainty in predicting such a complex system and provides a more realistic expectation. Reliable forecasters communicate this uncertainty transparently, helping us make better decisions about our daily lives. Finally, as we conclude our exploration of how weather works, it's vital to draw a clear distinction between weather and climate. We've spent our time dissecting weather, the day-to-day, hour-to-hour state of the atmosphere in a particular location. Is it hot or cold? Sunny or cloudy? Windy or calm? Is it raining today? Climate, on the other hand, refers to the long-term average of weather patterns in a region over many years or even decades. It describes the typical range of temperatures, precipitation, and other atmospheric conditions that characterize a specific geographical area over extended periods. Climate is what you expect. Weather is what you get. A single unusually cold winter day is a weather event. A trend of increasingly warmer winters over several decades, leading to shrinking glaciers and earlier spring thaws, is a climate change signal. While individual weather events can be extreme and fluctuate widely, climate patterns are more stable, representing the overarching behavior of the atmosphere in a particular region. Understanding this distinction is crucial for appreciating the broader shifts our planet is undergoing and for comprehending the profound challenges and questions that lie ahead regarding the future of our atmospheric ocean. So the next time you hear a weather forecast, take a moment to appreciate the incredible scientific endeavor behind it. The vast global network of sensors, the colossal computing power of supercomputers, and the skilled human intelligence that works tirelessly to interpret the atmosphere's complex language. Every cloud, every gust of wind, every drop of rain is a chapter in an ongoing story, constantly being written by the fundamental laws of physics and the restless energy of our star. We are not just living under the weather, we are living within it, an intricate part of its grand, mind-bending, and perpetually unfolding reality. And with this newfound understanding, perhaps you'll look up at the sky with a little more wonder, a little more curiosity, and a deeper appreciation for the magnificent, invisible ocean that cradles us all.